typical heating curve type problem. We're asked to fill in the blanks on the curve below, and the blanks are the question marks here. Calculate the energy required in joules to bring 170.00 grams of compound X, which has molecular weight of that, from minus 20.0 degrees to 75.0 degrees. So what we're looking at is this, where we're given some values and we're asked to find the others. But we're going to start out at minus 20. I'm going to show you how we get the 3400 joules to begin with. And that's going to be minus 20 is where we're going to start, or minus 20.0. And we're going to go up to this point here. So we're starting here, we're going to go to here. Now at this point what's happening is we're turning it in from a solid into a liquid, and that's going to occur at the melting point, which is going to be given here as minus 10.0 degrees. So what we're going to do here is we're going to figure out how much heat is required to make that transformation occur. So that's going to be Q equals mc delta T, and the mass here is 170.00 grams. The heat capacity, and we're looking at the heat capacity of the solid here, and there it is, 2.00 grams. Sorry, 2.00 joules per gram per degree Celsius. Now the important part of the temperature change is going to be from minus 20 to minus 10, so we're looking at 10 degrees, or 10.0 degrees Celsius. Now I want to point out here that this value is not negative, it's a change. It's a change in temperature, and the change from going from minus 20 to minus 10 is clearly going to be 10.0 degrees. So we do that and we figure it out. It's going to come out to be 3400 joules. Alright, so that's the energy required. That's how we get the 3400 joules here. Next we're going to figure out the heat here required to take the solid and turn it into a liquid. And what we're going to use there is the delta H of fusion. So the Q is going to be delta H of fusion, which would be the delta times the number of moles of X. Now the number of moles is going to be gotten from here. We've got 170.00 grams, and we've got a molecular weight of 85.00 grams per mole. So the number of moles would be gotten from this to be 170.00 grams times 1 mole over 85.00 grams, and that's going to come out to be 2.000 moles. Alright, so that's how we're getting that. Now we know the delta H of fusion we're given that is a molar heat of fusion, 2.00 kilojoules per mole, so that would be 2.00 kilojoules per mole times 2.000 moles. That comes out to 4.00 kilojoules. So that's the energy required to take it from a solid into a liquid. Now if we've got kilojoules here though, we probably want to convert that into joules, and the way we would do that is by doing this, and that's going to come out to 4,000 joules. The reason we're going to convert this into joules is because if you look at the question, it says calculate the total energy required in joules, and that's kilojoules. So in order to be able to add all these together at the end, we're going to need joule values for everything. Alright, let's see, number 2, we're going from the liquid at minus 10 degrees to the liquid at this temperature here. Now the temperature at this point is going to be the boiling point, because at this point we're looking at turning the liquid into a gas, and the boiling point is given as 60.0 degrees. So the Q equals mc delta T, we're looking at 170.00 grams, that's the mass of the substance, times the heat capacity. Now it's the heat capacity of a liquid, and the heat capacity of a liquid is 3.00 joules per gram per degree Celsius. And then we've got the temperature change. Now we're looking at a temperature change from minus 10 up to 60.0. Now the difference between 60.0 and minus 10 is going to be 60 plus 10, which is 70. So that's where we're getting 70.0 degrees from. It's a temperature change from the melting point up to the boiling point. And that's going to come out to be 35,700 joules. Now to get this one here, this is the heat required to take the liquid into a gas, and that's what we're going to be using is the heat of vaporization now. So the Q equals the delta H of vaporization times the number of moles. We already figured out the number of moles up here as being 2.00 moles, and delta H of vaporization is the molar heat of vaporization here, 3.00 kilojoules per mole. And that's times the number of moles, which is 2.000 moles. And just for kicks, we'll take it into joules as well at the same time. And that's going to bring us to 6,000 joules. Alright, so that's the energy required to take the substance as a liquid, turn it into a gas. Alright, that's where we get 6,000 from. Now the last part is to take the gas, which is going to be at 60.0 degrees, and heat it to this point. Well, what is this point? Well, this point is actually given by the end, which is 75.0 degrees. So I know that that's going to be 75.0. And we're looking at heating the gas, so we're going to be using Q equals mc delta T. The mass is still 170.00 grams. The heat capacity is the heat capacity of the gas, which is 2.50 joules per gram per degree Celsius. And then we've got a temperature change, and the temperature change is from the boiling point up to the end point of the problem, which is 60.0 up to 75.0, and that's going to be 15.0 degrees Celsius. And that gives us a grand total then for that part of 6375 joules. So then to figure out the entire amount of energy put into the system in order to take it from minus 20 up to 75.0 degrees, then what we're doing is we're going to take every energy that we've calculated along the way here, and we're going to add them together, and it's going to pop out to be 59,175 joules.